In my previous video, I did two things. I derived this equation, the magnetic field due to a loop of wire, along the z-axis. And then I did it numerically in Python to break it up into little pieces. And it was kind of awesome, I think. But I want to do really two things here. I want to show the functional relationship. I want to show that the numerical solution doesn't just give the right answer at one spot, but for all the spots. So that if I move along the z-axis, I get the same thing as this equation right here. That's the number one thing I want to show. Number two, I want to show the pattern of field in space looks like an electric dipole. Okay, so with those two jobs, I'm going to do them separately. I'm going to do the first one first. So let's jump over here. This is my previous program with the magnetic field due to a loop of wire. That's 100 little pieces of the wire in a loop. And that's the magnetic field at that location right there. Okay, so I don't want to ruin that code because it's great the way it is. Oh, and I did get the same. I get the same values. This is a vector value. Those are basically 0, and that's the z component right there. It's the same as the theoretical value, which I calculate down there. Great. Okay, so now let's copy this because we don't want to destroy it. There, and then let's do plot. Let's call this plot of magnetic field due to loop. That makes sense. And I don't want to draw anything. In this case, I don't want to draw anything. So, and what I also want to do is to turn this into a function. So let's go ahead and make our function. I'm going to leave that km out of here. That's my magnetic constant, that mu naught over 4 pi, which, you know, you should probably keep it in the loop, whatever, but let's call this def b loop. And what do I want to go into the loop? I want the radius of the loop. I want the current of the loop. I'm going to assume that the loop has the axis in the z direction. So I want the z value and n. So r is the radius of the loop. I is the current going through the loop. Z is the distance along the axis of the loop. And n is the number of pieces I break the loop into. So down here, that means I don't need this. Let's just put this, let's copy this stuff and put it up here. And let's call it RT. I don't like to have the variable names the same, even though it would work. Okay, so there's my function. I don't need n. Okay, so but what do I need? Do I need theta equals 0? No, because I never use that. That's old stuff. Do I need d theta? Yes. Oops. That was weird. Let's see. Okay, just tab that in. Theta start 0, yes, need that. N equals 0, yes. Observation location, yes. And you'll notice that here, if whatever I put in my function up here for z, I get z down here. Okay, so that's good. This r observation location, I do not need, because that actually draws a sphere, and I'm not drawing a sphere. B equals 0, I do need that. Okay, now this does the loop. And I'm going to calculate first, this RW is the location of each wire piece. I do not need this because that just draws a sphere and no one cares. I do need DL. Let's delete this. I do need DL. I do not need this arrow because didn't even need it then. Let's delete that. I do need this R equals R0 RO. That's the vector from the wire to the observation location. And I do need this. And now you'll notice I, that's passed from the loop call. And then DL, I calculate. I think everything looks good. Okay, and then I add that to the total magnetic field. I update N, and done. I'm not done. I need to return B. Yep. Okay, so let's just try this. Up here, I'm going to say print B of R was 0. Let's just put this as RT. I got to have it in the same order. IT, ZT, and 100. And then let's just change this to, I have to change this to T, 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 T. And that should work. And then this stuff down here, I don't want to do. I'm not going to make an arrow. Okay. Save it. Run it. Error. Can't find variable b. Oh, b loop. Okay, so there's my, that's the same thing I was getting. So what all I've done so far is to make this calculation as a function. Now I can move my z value and find the value of the function at different places and make a graph. So let's start off with a graph. So let's say t graph equals graph, object graph. Graphing is great in Python. I'll include a link down below. So graph, I need the title. B due to loop. X title, that's the, in the x-axis on the graph, is going to be equal to z. Y title equals bz in Tesla. Now I'm going to have two graphs I want to plot. Let's call it fn equals g curve, color equals color.blue, and I'll label that as numerical. Label equals numerical. That's my numerical solution. And then ft is going to be g curve, color equals color.red, label equals theory. Okay, so now leave that function alone. I don't really need this stuff anymore. Let's just comment that out. Now where do we want to start? Let's go ahead and start at z equals 0. So I'm going to say zt equals 0. And dz is going to be the step size. How far do I move? So if I want to, let's say this is a 0.001. I don't know, I'm picking up stuff. Okay, so now what I can do is to say while zt is less than, how far do I want to go? Let's say 0.05. I'm just picking stuff. The first thing I'm going to want to do is to calculate the theoretical thing. So let's just copy this. It's right here. No. What did I do? I just want this. Just that one. Copy that. There. So there's the b theoretical. And let's say b num is b loop. I don't even actually have to do this, but I'm going to. So let's go, what do we call that? RT, IT, ZT, 100. Yep. Now let's plot the values of these. So I'm going to say fn.plot. Its x coordinate is going to be zt. Its y coordinate is going to be bnum.z. Remember, that returns a whole vector value. I can't plot the whole vector value. I just want the z component. And now for the theoretical, I can say ft.plot zt and then just b theory, because that was just a scalar calculation. Finally, I need to increase my value of z. zt equals zt plus dz. And that should do it. Save. Run. Okay. I think they're right on top of each other. Let's do something crazy. Let's change this to down here 10. It's still the same. Let's say 1. Huh. It's the same. I think there are two lines there, which can't be the same. If there's only one piece, what if there's two pieces? See, which one? It's not plotting. Okay, here's what we're going to do. Let's change this. Something's wrong. Let's change this to 100. And let's go and not plot the theoretical. And then we can just see. Okay, it's just right on top of each other. That's crazy. Okay. Huh. Wow. Why is it right on top of each other? It shouldn't be. I mean, it should be close. It is close. Well, I guess because the Z, I'm thinking about if you have like something crazy, like just one piece of the wire off to the side, its Z component is still going to be the same value. It's just going to also have an X component. The X component's not going to cancel. The Z component was correct. So I think that's why. So I think that it works no matter what. Okay. So that's that. We did that. I'm happy with that. Now let's go to the second part. So let's save this. I'm going to give you the link to this code. Don't worry. Save that. This is a program that I wrote, which I will also give you the link to. And this is the calculation of the electric field due to a dipole. So here I have a positive and a negative charge right there. And then I have different locations around here that I'm plotting the electric field. Okay, so what I did was, this is just for my dipole. That's for my dipole. This R is that's the radius of the circle, right? And then this is the number of data points I have it into. And then this is what I'm doing the same thing I did before. I'm starting right here and drawing a circle moving around X number of times, and then I have a scale too. And then what I do is just I calculate the observation location. I use that to calculate the electric field. And then I calculate the electric field to the negative one, add them together, draw the arrow, and then that was it. And then I did it for 2 circles. So let's just do that for 1 circle. Oops, zoomed in too much. Okay, but I mean, it is important to notice the pattern here. Not the exact shape, because we're going to have ours bigger. So let's go back over to the previous program, magnetic field due to a loop, and run this. Just make sure that's the one we want. Okay. So now let's copy that, and let's say magnetic loop dipole field. It's weird. Okay. Saved it. Okay, so now we can edit this program. We won't change that other one. I really should. I should have that other one too. Because I could use that function, right? That function's really great. Let's steal that function and fix it. So I'm going to go back over here. Let's say my trinkets, magnetic field, plotting solutions, plot a magnetic field due to loop. That's it. Okay, and I'm going to copy this, because that returns the magnetic field, but I'm going to need to change it. That's not what I want. I want this one. Okay, so let's just put this up here. There's my loop. Now, I'm going to add something in here. I'm going to add, put it right, instead of Z, I'm going to put RO. So RO is the observation location. Yeah, that's what I'm going to do. And so I'm going to get rid of this, because it's part of the thing. And then everything else looks fine, right? I don't need these. Well, I do. I'll call them RT. IT. I don't need that. Okay. Let's get rid of all this stuff that just does the same thing. Oh, wait. No. Yes. So I'm going to do 2 things. I'm going to draw the loop and calculate the loop. Yeah. So I'm going to have that function to calculate the magnetic field. This stuff I don't need to I just want to draw it. So I don't need that. I don't even need that. That's fine. And then, so let's just get rid of all this. So now what I want to do is to use, this is getting a little messy, but I think it's okay. So go over here, and I'm going to do the same thing. I'm going to say R and theta. I have another theta, right? I'm going to use a different theta. R is some value that's going to be bigger than that, and it is equals 16. So let's say RT equals, let's say 0.05, theta 2 equals 0. Looking over here. N equals 16. N equals 16. D theta 2 equals 2 times pi divided by n. Oh, I have another n. Nt. See, this is what happens when we reuse code. Things start to get a little messy. Okay, so what I'm going to do is to move my observation location again. Okay, so I'm going to say, let's just do this exact same thing. While theta is less than 2 pi. I feel like I'm getting out of control here. RO, this is the same thing, except not. Except I'm going to change this to theta 2, and RT. I know that's weird. Next, I'm going to all this does is to calculate the magnetic field, or the electric field. So I can say B loop, B temp equals B loop, and then I'm going to say RT, IT, RO, 100. Look at my function. RI, right. Okay. And now I can draw my electric field arrow. So B scale, I used before 1 times 10 to the 4th. So let's just put an arrow there. So arrow, position equals RO. Axis equals B temp times B scale. And let's make it psi n. And then I need to, what did I do over here? And then I increase theta by d theta. So I can say theta 2 equals theta 2 plus d theta 2. And then that's it. I feel like I'm doing something wrong, but let's just run it. Let's see what happens. Save it. And run it. And it didn't work. Couldn't find the variable z in my right here. Is there a z up here? So where, maybe it's my B loop. Do I have a z? No. Down here, do I have a z? Where's z at? Okay, looking for z. I thought I got rid of the z. RO. Do you see the z? Where do I call z? There it is. I don't even need that. No. POS must be a vector. RW is a vector. RO. See, I don't know which one this is referring to. RO. Oh, so up here I don't have an RO. ROBS. I don't even need that either. Can't find the variable R. It has to be RT. RT. I have 2 RTs. Well, that's fine. Doesn't really matter. Okay. Can't find the variable R again. Just making all sorts of trouble here. Okay, I think I'm just mess this up so bad. Okay, I'm gonna stop because I think I'll have to come back and finish this one. I think I'll give you the code. I did some while in. I never increase in. Oh, I see. Oh no, I did right there. So something happened here that I didn't like. I'll go back and redo this, and I promise, okay? But I've already made a video that is longer than I want. The first part I'm still happy with. I'll do this other one part later. I'll talk to you guys later. I feel like I let you down. I'm kind of letting myself down right now, too, so it's good.